You're staring at white clouds far, far below your plane when you hear two flight attendants talking nearby. They sound terrified. Another moment, and they aren't standing in the aisle anymore. They're, you rub your eyes, floating in the air, along with almost half of the passengers on the flight. The only thing preventing you from joining them is your seatbelt. Huh, following the rule, keep your seatbelt fastened while seated, pays off. Soon, you hear the captain's strained voice.
"Dear passengers,"
he says,
"we've accidentally left Earth's atmosphere and reached outer space. Please try to be careful while floating around."
Ah, well, it explains a lot, you think. Flight attendants are trying to pretend nothing is out of the ordinary. They're floating along the aisle, holding on to headrests and hand luggage compartments. At one point, they attempt to serve lunch, and people all over the cabin find out that orange juice looks very pretty in weightlessness, bright bubbles of different size. At one point, you decide to get all the perks and unfasten your seatbelt. Woohoo! That's fun, but also quite scary. You can't control your movements. You just float wherever a draft takes you. Sometimes you bump into other passengers, the food that's escaped the catering cart, the carts themselves, books, laptops, jackets, everything that wasn't secured in place when the plane left the atmosphere. That's probably not the safest thing, but since the speed isn't high, you come out of such encounters unscathed. If this trip lasts long enough, you'll probably have to get used to the lifestyle astronauts lead on the ISS. Let's say you suddenly become homesick and start crying. Then, your tears won't roll down your cheeks, falling down onto your t-shirt. They'll remain on your eyelids, burning them. You won't be able to take a shower, since water will simply form tiny bubbles and float away. So, you'll need to use special wet wipes to remove all that dirt off your body. Oh, and by the way, you won't be able to wash your clothes. You'll just have to throw them away, like astronauts on the ISS do. You'll also have to use edible toothpaste and shampoo that doesn't need rinsing. If your plane remains in space long enough for your hair to grow out, you'll have to use special scissors equipped with a tiny vacuum cleaner and a container. This way, your hair won't scatter all over the place. Imagine someone inhaling it. Uh-oh. You look around the cabin and observe a very funny phenomenon. Your fellow passengers rotate, suspended in the air. At certain intervals, they suddenly change their axis of rotation by 180 degrees, and it repeats again and again. The miracles of zero gravity. Suddenly, you spot a spider. What's it doing on this flight? Apparently, spinning its web. But since the tiny creature has to do it in weightlessness, the web is very irregularly shaped. It looks a bit like a ball. Suddenly, you feel some itchy sensation in your nose. Oh great, you're about to sneeze. Achoo! Some powerful force pushes you backward, and, disoriented, you crash into a wall. Everything goes black. Unfortunately, should your plane really get into outer space, your adventure wouldn't last long, because planes are simply not designed to fly in space. The average cruising altitude of a commercial airplane is between 31,000 and 38,000 feet, which is pretty high. At this altitude, the air becomes thinner. As a result, aircraft can travel more easily and, even more importantly, burn less fuel and save more money for airline companies. They cannot fly lower, but neither can they fly higher. As soon as a passenger jet takes off from an airport, the first thing pilots do is to lead the plane as high as possible and as fast as they can. The average airplane usually reaches its cruising altitude of 6 to 7 miles in the first 10 minutes of the flight. At the same time, each airplane has its own cruising altitude based on its weight and some other characteristics. For example, the famous supersonic passenger airliner Concorde, whose maximum speed was twice as fast as the speed of sound, used to fly way higher than other modern-day planes. at 50,000 to 60,000 feet. When planes fly at the height of 35,000 feet, they manage to avoid bad weather. For example, high winds and heavy rains ranging in the lower layers of the atmosphere. Plus, such rather high altitudes allow planes to avoid heavy airborne traffic, like helicopters and light aircraft. It also helps them stay clear of birds and big insects. And finally, and most importantly, if an emergency happens at the height of more than 6 miles in the air, pilots will have enough time to figure out the best solution. Okay, I get it. The higher, the better. But then, why do planes avoid moving past their cruising altitude? You see, when a plane is flying very high, it needs more time to get back to a safe altitude. And during such emergencies as rapid decompression, every second counts. Also, while traveling at such great heights, aircraft crews can't communicate with the ground services as efficiently as they do at the regular cruising altitude. The higher you get, the thinner the air becomes. That's not a bad thing, unless an airplane climbs too high. Then, the air can get too thin to provide enough lift to keep the machine in the air. It's the difference in air pressure that creates the necessary lift. But if the altitude is too high, this difference is almost non-existent. Also, if a plane rises too high, oxygen becomes too sparse to fuel the engines. A plane gets less and less air the higher it climbs, and at one point, it doesn't have any more power to keep rising. Unfortunately, it can lead to a disaster. While flying at lower altitudes, airliners can rely on the assistance of the wind. But that high up, they have to waste too much energy and fuel to stay aloft. And don't forget about the weight of the aircraft. The more the machine weighs, the more difficult it is to bring it to a certain altitude. On the other hand, if, instead of boarding that Airbus 380-800, you decided to choose the X-15, you'd see a bit more of outer space. Most people have the wrong idea of space. They think it's something very distant, something you need to try hard to reach. Outer space doesn't begin at some particular altitude above the surface of our planet. But for convenience, it was agreed that the imaginary boundary between Earth's atmosphere and outer space, also known as the Kármán line, should be at the height of 62 miles above sea level. So, back to that rocket plane, the X-15. It was designed in the mid-50s and made its first journey in June 1959. It had very thin and quite stubby wings to get as much lift and stability as it could. It traveled at more than 5 times the speed of sound, and it was equipped with a cutting-edge rocket motor. Its power output could be changed, and then the engine of the spaceplane could function like that of a conventional aircraft. The X-15 needed special fuel that contained a lot of oxygen. The plane could reach an altitude of 62 miles, which means it did reach space. Anyway, imagine you were to pilot that miracle of a plane. During the first stage of your journey, your aircraft would be carried and then drop-launched from under the wing of a B-52 mothership. You would definitely feel the drop. It would be quite abrupt. The X-15 would be a very busy airplane to fly, but also very exciting. You'd be able to do some sightseeing at the edge of space, but you wouldn't likely have much time to soak up the view, since you'd be pretty busy controlling your supersonic flying machine. You'd have to be very attentive and watch for any deviations. When it was time to re-enter the atmosphere and get back to Earth, you'd have to make sure the plane was lined up perfectly. Now, just relax into your window seat on an absolutely regular flight. Maybe one day, people will use planes to fly to space, but not today.
You know, back in the 1970s, scientists discovered a mysterious gravitational anomaly called the Great Attractor. Wait a minute, I had that nickname in high school. Anyway, it's a place in the sky that draws hundreds of galaxies, including our Milky Way. You won't be able to see it because it's on the other side of the Milky Way, 150 million light-years away. The Great Attractor actually lies in the direction scientists usually call the zone of avoidance. I have one of those too. It's my closet. Now, there's so much dust and gas in this region that we can't see what's happening there. That area blocks most of the visible light from beyond, but all that dust and gas don't block X-rays and infrared light. So, as X-ray astronomy developed, researchers could finally start to observe all the objects within that area, including the mysterious force attracting everything. But so far, no one has figured out why it's happening. Our moon may be 200 million years younger than we previously thought. Many scientists believe that the moon formed during a powerful collision between our planet and an unknown Mars-sized body. The molten dust and debris got together and formed a new object we know as the moon. The lunar crust was probably going through a process of solidifying over a couple of 100 million years. Did you know about an early magma ocean on the moon? Scientists realized it was a real thing after they had discovered big amounts of the lightweight mineral called plagioclase. This material usually crystallizes and floats to the surface of magma. Anyway, this mineral was 4.36 billion years old, which means it formed 200 million years after the first solid materials had appeared in our solar system. Thus, the theory that the moon formed during this giant chaotic collision might be true. Now, if you stand on the moon one day and leave your footprint on its surface, it can stay there for 1 million years. You'd also see the footprints of other astronauts, even though no one has landed on the lunar surface for decades now. The moon doesn't have a full-fledged atmosphere. There's no breeze or anything else that can sweep up the dust and erase the footprints. We see it as a small dot somewhere in the distance, but in reality, the sun is so big that if it were an empty ball, you could fill it with more than 1 million Earths. The sun makes up 99.86% of the mass of our entire solar system. Another enormous object in our solar system is Jupiter. It's 11 times wider than our planet. For example, Earth isn't even the size of the Great Red Spot. This enormous storm has been raging on Jupiter for more than a century. And no, it's not anchored to anything solid, since Jupiter is a gas giant. It's like a massive hurricane, oval in shape, reddish in color, and wide enough to engulf our home planet. Once upon a time, it was 3 times as wide as our planet, but over the last few centuries, it's been shrinking as well as growing taller. As for Jupiter, this gas giant is some sort of vacuum cleaner that keeps our solar system safe. Jupiter has incredibly strong gravity that eats up comets or asteroids that might potentially harm our home planet. In some other planetary systems, gas giants similar to Jupiter migrate from the position where they formed. They spiral inward and come closer to their parent stars, and as they travel, they swallow up small rocky planets. Or their strong gravitational force flings these planets out of their star systems. Luckily for us, Jupiter's gravitational force doesn't work that way. If Jupiter-like planets stay away from their stars, they keep their planetary system safe, protecting those small planets in their inner orbit. Jupiter, for instance, can change the orbits of small space bodies that come too close to the inner planets of our solar system. That's why this gas giant is a good guardian of our solar system. Now, there's a supermassive black hole that roams through space at a speed of 3 million miles per hour and leaves a trail of debris behind. Hey, I had a little brother who once did that. It's about 1 million times as heavy as our Sun and, at the moment, 2 billion light-years away from Earth. This black hole started like any other, in its own elliptical galaxy with many stars surrounding it. Supermassive black holes often form and remain in the center of galaxies. But this one got away. One theory claims that this black hole is different because the galaxy where it formed may have bumped into another galaxy at one point in the past. Sometimes galaxies merge into a new one if this happens, but not this time. Instead of merging, the black hole's galaxy passed through a way bigger one millions of years ago. That giant galaxy already swallowed up some other galaxies along the way. And since it was so large, the galaxy surrounding our supermassive black hole ended up ripped apart. The black hole at its center managed to run away with some of the nearby stars. That's what left a burning trail stretching across the surrounding space. Solar superstorms are so powerful that they can cause blackouts all over the world. Random flares coming from the sun cause solar storms, and they can really happen at any time. Back in 2012, we were lucky because the strongest solar storm in over 150 years passed very close to us. It just tore through Earth's orbit. If it had happened only a week earlier, our planet would have had to deal with tons of terrible consequences, including power outages all over the globe. Gamma-ray bursts are strong enough to destroy planets. We're talking about extremely strong bursts that mostly occur in galaxies very, very far away. If these rays are pointed directly at some space object, they can completely wreck it, even if we're talking about an entire planet. So Earth is safe for now, and we have nothing to be afraid of. A gamma-ray burst happens in our galaxy approximately once every 5 million years. Luckily, it occurs too far away and doesn't affect life on Earth. That's what I call irrelevant, but still scary. A burning ice is a thing. It may be hard to picture it here on Earth, but one strange planet called Gliese 436b is literally a burning ball of ice. It's covered with ice, but at the same time, it has temperatures of 822 degrees Fahrenheit. You can't actually see the planet burn, since there's too much water on the planet. It's because of the strong gravitational force that pulls the water molecules to the core of the planet and packs them together incredibly densely. That way, water molecules can't evaporate, which is why the ice on the planet's surface doesn't melt. There are stars that can munch on other stars. These space objects are mostly smaller stars with a lower mass. They target the closest stars and begin to absorb their hydrogen fuel to boost their own mass and generally live longer. A vampire star becomes strikingly blue. It also gets hotter. This way, it seems that it's way younger than it actually is. If a star, or basically any other object, falls into a black hole, it gets stretched like spaghetti. This process is even called spaghettification. The gravitational force of a black hole stretches an object in one direction, but at the same time squeezes it in another. And telescopes have captured such a process a mere 215 million light-years away from us. An unlucky star was wandering too close to a supermassive black hole at the center of a galaxy. The star, which was approximately the same mass as our Sun, didn't stand a chance against the extremely strong gravitational pull of the black hole. After all, the black hole we're talking about was over 1 million times as massive as our star. Astronomers were lucky to record this event, because after a black hole eats a star, it often spits out its material in the form of dust, so it's hard to see what's going on there. Anyways, this picture of the black hole, was it a spitting image? Hey, what did you expectorate? Okay, I'll stop now. In space, no one can hear you scream. Or is that, in space, no one can hear ice cream? Well, either way, we know that no supernovas, crashing asteroids, and burning planets make a sound in space. Or do they? What if you actually can hear something out there? Well, let's see. Okie dokie, back to middle school. Sound is a mechanical wave originating from vibration. What exactly does that mean? Well, the simplest example is guitar strings. Let's pluck one of them. It starts to vibrate. The atoms inside the metal string begin to push and beat the atoms of the air around them. So now, atoms are constantly pushing each other until they reach our ears. It's like a wave from a pebble thrown into a pond, and it happens very quickly, at a speed of about 761 miles per hour. Then our eardrums begin to vibrate at the same frequency, and the little bones inside our ears transmit this vibration to the brain. The brain then does its magic, recognizes the pattern, and turns it into sounds. Great! Now we know that we need some particles to create sound, and we can find these particles in gases, liquids, and solid substances. And what about space? Nope, it's almost a perfect vacuum. And you've probably already heard that there's no sound in space because it's a vacuum. But what does it actually mean? Well, a vacuum is a perfect void. It's an area completely devoid of matter. It means there's nothing there. Yeah, despite all those celestial bodies in space, there's actually no air in between them. No atoms, no particles, nothing, nada, zippo. Well, almost. To be honest, the perfect vacuum doesn't really exist. We can't get rid of atoms for good. But space is very close to this notion. On average, there are 15 to 80 atoms per 1 cubic inch. This may sound like a big number, but keep in mind that these atoms are tiny, and the void distance between them is huge. For comparison, 1 cubic inch of air contains about 16,000 atoms. So, of course, with such a low density, these atoms can't push each other. Even if the vibration is very strong, like, a supernova, they still won't be able to do that. So, movies have been lying to us. All these epic space scenes actually take place in an awkward silence. Who would have guessed? But don't get upset. What if I tell you there are, in fact, some ways to hear sound in space? First of all, there's still sound on other planets. If there's an atmosphere on a space body, or at least something like gas, water, or a solid surface, there will be sound. In our case, the atmosphere becomes completely silent at about 60 miles above the Earth's surface. That's where the sky stops being blue and a black starry veil begins. In any case, we'd have to land on another planet, or at least get close to its atmosphere to hear something. But whatever it is, it would sound very different. Let's take our favorite Venus as an example. The atmosphere there is very dense. Scientists jokingly call it a thick chemical soup. No thanks. So, if you somehow managed to stay alive and speak there, your voice would be very different. It would become much louder, and it would sound deeper. So, if you want a pleasant baritone, you know what to do. I wonder what would happen if Earth had a denser atmosphere. What would we hear then? Well, you can vaguely imagine that if you've ever been in the water. Water is very dense. Sound moves there much faster and better compared to the air, at a speed of almost a mile per second, depending on the water temperature. So if you sit in an empty room with no sound sources, you won't hear much, right? Now, dip your head in the water and check out how the same silence sounds here. It's not quiet at all. Even if you ignore the ever-present sounds of the water itself, you'll immediately notice how well you can hear your own body, how your blood pulsates in the veins, how your heart works, the slightest movement of your fingers. Kinda creepy, isn't it? This gives us an idea of what would happen to us on a planet with a denser atmosphere. And that's just crazy. We would hear everything. From scurrying animals to the movement of tectonic plates. Come on, you'd probably say. It's obvious that there's sound on other planets. But didn't you say we can hear something in open space? Actually, yes. For example, in a cloud of dust. You can find space dust almost everywhere in space. It may be the remains of a star or something else. And in these places, everything is a bit denser than usual. This means there are probably dust clouds where particles are very close to each other, which means they can produce sounds. Of course, those will be very quiet and transmitted over a very short distance. But it's better than nothing, right? Plus, we already have one real space sound recorded. It came from the Perseus galaxy, which is located 250 million light-years away from us. NASA recorded it in 2003. Those of us music geeks will want to know that it's a B flat, 57 octaves below middle C on the piano. You'd have to add another 660 keys to the left on the keyboard. But its frequency is so low that the human ear unfortunately can't hear it. But besides that, we can only hear something inside spaceships. These are small pockets of air, after all. In a spacesuit, you would hear sounds very well, too, including your breathing or blood circulation in a spacesuit. But two astronauts flying side by side wouldn't hear each other, even if they got very close and shouted very loudly. It's quite funny. If you, being an astronaut, bumped into something, it would be very loud for you, but your friend wouldn't hear anything. That's why astronauts use radio devices.
2091, cancel your call, 2879 will handle.
Now, purely theoretically, if you could somehow crawl out of your spacesuit and survive, you'd be able to hear the chatter and noises going on inside the spaceship. But how? So look, we have some air inside the spaceship and it transmits sound. It reaches the metal casing and gets through it. And then, if you leaned against the ship, preferably touching it with your elbow or knee, the sound would be transmitted to the brain directly through your bones, ignoring the ears. Yes, our bones conduct sound. That's how, for example, deaf people listen to music. It's called bone conduction. It's used in some headphones and some other technologies. You can do a little experiment. Hold your fingers over your ears. Shut them properly so that you really don't hear much. Then try to touch a sound source. It can be anything vibrating. For example, a speaker playing music with some part of your body where the bone is close to the skin. Now, watch the miracle happen. You can hear the sound not through your ears, but directly in your brain. But please, don't repeat this experiment in open space. Ice cream? Haha. Now, you've probably heard about things like the sounds of space, where you can listen, for example, to the sounds made by the sun or different planets. How do we record these ones? Easily. There is another way to hear sound in space: electromagnetic waves. In other words, a radio. Radio is the same form of electromagnetic radiation as light. These waves can travel in a vacuum without any problems. Astronauts' transmitters work that way. An astronaut says something to their friend. The sound waves turn into radio waves, reach the other person, and are then converted back into sounds. And this is how we get so-called space sounds. Our planet is actually very loud in that regard. We're sending a huge amount of radio waves into the universe, all radio signals we've ever listened to. It's a pity that they travel only 110 light-years away from us. But I think it's good that we don't hear everything that happens in space. Imagine if sound could easily travel through the universe. We would hear everything, from solar flares to nearby supernovas. Horrifying, right? So maybe we're just lucky. Hey, remember, in space, you can hear ice cream. Chocolate! Vanilla!